So the delay problem is insert interval. And if you caught a glimpse there, the acceptance rate is very low. That's pretty typical for binary search problems because there's a whole lot of corner cases and finicking. For that reason, I'm not the biggest fan of these, so I'll just quickly outline what I did and the intuition behind this problem, and then the specifics are up to you. So we can see it's problem 57. It's a pretty standard problem, one of the first to be made. You can pause to read the whole thing, but the idea is we have this list of intervals. So we have an interval between 1 and 3, an interval between 6 and 9. They're non-overlapping, so we can't have like 1 and 3 and then 2 and 9. They're all distinct and they're all in ascending order. We have a new interval we want to insert. So here, 1 and 3 would overlap with 2 and 5, so that new interval would be 1 and 5. And then 6 and 9 is unchanged. For this one, we're inserting 4 and 8, so we can kind of see, well, 3 and 5 4 kind of gets in the way there, and then 6 and 7 is within that, and then 8 and 10 also intersect. So eventually we're going to have 1 and 2, and then this is all going to be merged into 3 and 10, and then 12 and 16. So the first thing I do is I just cover some corner cases. If we're not given any intervals, if intervals.length is 0, just return the new interval in a list. Because that's the only interval now. If the new interval is beyond the last interval, so if the bottom of the new interval is greater than the top of the highest interval, then just append it to the end of intervals. And also the opposite. If the top of the new interval is before the bottom of the earliest interval, then append it in the other order. So then I use bisect left. It's like a Python binary search built-in function. And I say we're going to run 2 binary searches here. So we're going to first run L for left, and we're going to use this as a binary search. We're going to use the low end of the interval of our new interval as the binary search. And we're going to look for what's the last interval that isn't affected by the new interval, or actually rather it's what's the first interval that is affected by this new interval, whether that means it's overwritten or it's intersected with at all. And then I say, well, if we're intersecting with it at all, that means that no matter what, the new interval is either going to, let's say this was 0 and 5, where this L would return 1 and 3, and then we would look at it and say, well, if this was 0 and 5, then we want to keep it 0 and 5. But if it's 2 and 5, we want to take the minimum and say, now it's 1 and 5. So we're pretty much here just saying, change new interval. Change new interval to be the minimum between itself and this. And you can see my disdain for this problem because my code isn't even that cohesive. This could have been a minimum function instead of an if statement, but I really didn't feel like doing all that much finicking tonight. And then we do the same thing for the right side. So we take this 5 and we say, what's the final interval that's affected here? And this one actually, again, I should correct myself and say if I printed L and R here, this is actually, I'm using bisect right, and it's actually saying, we can see 0 and 1. So it's saying what's the final interval what's the first interval that isn't affected by it? So 6, 9, and then if there was a bunch of stuff forward, we can see in the end eventually what we're going to do is we're going to just insert the new interval by saying take everything up to but not including the first, as we predefined for this L, the first interval that's affected by new interval, add in new interval, and then add in everything else that's after the new interval that isn't affected at all. And that's pretty much it. I mean, the only other line to look at is just like we did for L, we say, hey, if let's say this was 6, if new interval intersects with the previous r minus 1 here, if new interval, the last thing it intersects with, if that thing has a greater maximum than new interval, then that's new interval's new maximum. So here, when we have 2, 6, we're actually taking this maximum and we're taking this minimum here. And maybe for the sake of simplicity, I'll just change this right now and say new interval at 0 equals min, new interval at 0, intervals at L at 0. So we take the minimum, we say 1's smaller than 2, so the new interval is going to have a 1 at the start. And then we say, hey, this technically intersects because we can't have, if they're the same, then they count as intersecting rather than not. So then we say, well, 9 is greater than 6, so what we're going to wind up with is 1, 9 in the end. And in the end, that's what we're given. And there's a bunch of corner cases of if this was 6, if this was 7, if this was 10, and it's beyond that, then we still are taking the maximum. So this is actually, in my mind, a pretty elegant solution once I've changed this if statement to be more symmetrical. But it's not particularly fast. I mean, it seems to do above average, but I guess everything does, because probably down here are like linear solutions. The first non-tree problem that we've been given in like a week or so. Hopefully it's not too frustrating or difficult for anyone.